Hey everybody, Dr. A here, and in this video we're going to be providing some background information on center of gravity, center of mass, and centroid. And we're going to be referencing the Hibbler Statics textbook published by Pearson. Now, before we dive into it, I want you to remember to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
In this video, we're going to be discussing the concepts of center of gravity, center of mass, and centroid. Now, mathematically, these three concepts are essentially the same thing, but physically they are three unique entities, okay? But we're going to start with the mathematical basis of these concepts, and we'll see that mathematically speaking, when we have to do any kind of calculation involving center of gravity, center of mass, and something called centroid, it is mathematically, they are basically the same as one another. So let's go ahead and call this a mathematical framework, okay? And in order to set up this mathematical framework, we're gonna say let's consider a one-dimensional center of gravity illustration. Okay, so here's what I want us to do. I want us to consider the following. Let's say that we have some kind of positive x-axis and we have an origin over here on the left. Okay, and let's say that we have several objects that lie along this x-axis that each have their own weight. So let's call this weight number 1. We'll of course call this weight number 2. We'll call this weight number 3. And let's say we can have as many of these as we want. So let's call this one weight N, okay? Not number 4, but N. So that represents that we can have as many of these weights as we want. We could have 1, 2, 5, 7, a million of them, whatever, okay? Now, let's look at their relative location to point O, all right? So let's say that weight 1 is a distance x1 away from the origin. And let's say that weight 2 is a distance x2 away from the origin. And then, of course, we're going to say weight 3 is a distance x3 away from the origin. And then we're going to say weight n is a distance x sub n away from the origin. So each one of these weights has some kind of distance away from the origin. Now, if you're looking at this, you may be thinking, well, wait a second, this looks awfully like what we would call perpendicular distances. So you're right. So keep that in your back pocket for now. Now, let's go ahead and write an equivalent system. So I'm going to put a little arrow here. I'm going to say, let's write this system as an equivalent system over here on the right side here. So let's say we have the same origin here and that same x-axis, okay? And let's say that we have this total equivalent load right here. We're going to call this W total right here, okay? And guess what? W total is going to be the sum of all of these individual weights, okay? So we're going to say the total weight, of course, is just if you add up all of the individual weights from I goes from 1 to N for N number of weights, okay? So that's our equivalent system. Now let's go ahead and say that our equivalent total weight, W sub t, is some distance x bar away from that origin. All right. So again, we're looking at an equivalent system here, just like we've seen in some of our previous theory. All right. So here's a few things we can write about this equivalent system. All right. The first thing we can say is, of course, this statement right here, the total weight is equal to all of the individual weights added up together. No question about that. But what about this? We can actually write a moment equilibrium equation for this original system as it relates to the equivalent system. All right? And here's how we can do that. We can say that the sum of the moments about point O, counterclockwise is positive, equals the resultant moment about point O, okay? Now, how do we piece this together? Well, guess what? This left part of the equation is from the original system, and then the right side of the equation is from the equivalent system. So again, this left side of the equation corresponds with this original system, whereas the right side of this equation is going to correspond with this equivalent system. So how can we write all this together? Well, if we say the sum of the moments about point O, think about it. What's the sum of the moments about point O? Well, that's going to be W1 times X1 plus W2 times X2, so on and so forth, right? So how about we write all that out? How about we say, if we say sum of the moments about point O, and in fact, if you want to be mathematically proper, you can even say as I goes from 1 to n, and you can say sub I here for n number of moments that are happening if you really want to be mathematically proper, okay? So how can we write this all out? Well, if we look at the left side of that equation, we're going to say that this is the same thing as this. So we're looking at the left side now. We're saying that's the same thing as the sum of W sub I times X sub I, all right? Right? Because that's W1 times X1 plus W2 times X2 plus W3 times X3, so on and so forth, all right? And if we're saying counterclockwise is positive, then based on this illustration, this happens to show clockwise moments everywhere. So we can put a negative out in front right there because each one of those happens to be a negative value in this illustration, all right? And of course, we could say I goes from 1 to n, and that's the left side of the equation, right? So what about the right side of the equation? Well, the right side of the equation, the resultant moment term, corresponds with this equivalent system. So what do we have here? We have the total weight times x bar, causing a clockwise tendency of rotation. So that will be a negative as well. So we would say minus W total times x bar. All right. Now, of course, we can look at this. The two negatives will cancel. All right. Both of these are showing the same directionality. In fact, you can even put a little direction sign up here on the right side of that equation. So in both sides of the equation, we'll make a note here, both sides of equation counterclockwise is positive. All right. So let's do a little bit of rearranging now. We can rearrange this and we can solve for x bar. And what do we get? We get the summation as I goes from 1 to n of W sub I, x sub I, all divided by W total. Well, what was W total? We wrote that as this summation term. So we could write this as summation I goes from 1 to n, W sub I, x sub I, divided by summation I goes from 1 to n of W sub I. And this right here is our mathematical framework for the location of any of these things: center of gravity, center of mass, and centroid. Again, we call this a mathematical framework, all right? So it turns out that whether you want a center of gravity, center of mass, or a centroid calculation, you can use this basic formulation. Now, we also said in this mathematical framework, we considered a one-dimensional center of gravity illustration, okay? Now, this can be extended into 3 dimensions, all right? So for 3 dimensions, we, of course, we know x bar, we just wrote that, right? Summation I goes from 1 to n of W sub I, x sub I, divided by summation W sub I goes from 1 to n. And what else are we going to have? We're going to have a y bar as well. If we had a y dimension or a second dimension to this, we would have summation I goes from 1 to n, W sub I, y sub I, divided by the same denominator, summation W sub I goes from 1 to n. And then for a third dimension, z bar, we would have summation I goes from 1 to n, w sub I, z sub I, divided by summation, same denominator, w sub I goes from 1 to n. And this is how we extend this concept, this mathematical framework, into 3 dimensions. So this framework, we're going to make a note here, we're going to say this mathematical framework can be applied to all 3 of these topics that are built into our title of this video. Can be applied to center of gravity, center of mass, and centroid. Now, my question, and this is for you to think about, is what are the actual definitions of each one of these terms? Well, it turns out these 3 definitions are very similar to one another. They just refer to different physical entities. Okay, so let's give a brief definition of each one of these. What is center of gravity? Okay, what is center of gravity? Well, this is the point of application for the total weight of a collection of particles, which we call that a discrete system, or a continuous body, which of course is called a continuous system. Okay? So again, it's basically where the total weight of either a collection of particles, like we saw in our mathematical framework, is acting, or if you have a continuous solid object that maybe is a weird shape, or it doesn't have to be a weird shape, just any solid object, we call that a continuous body. Okay, so it's the point of application of where that total weight is acting. All right, now center of mass. What is the definition of center of mass? Well, center of mass is very similar. Center of mass starts out the same. The point of application for the total mass of, and then the definition is the same definition as before, ... So point of application for the total mass of a collection of particles for a discrete system or a continuous body. And then centroid, again, has a very similar meaning. Centroid is the geometric center of an object or collection of objects. So this is the geometric center of an, we'll say, of a collection of objects for discrete systems, or a continuous object. Now, the thing about centroid is when we're talking about centroids of objects, we're often concerned with either lines, areas, or volumes. Okay, so we're going to put ... and we're going to say often are lines, areas, and volumes. Okay, so when we look at centroid, we're going to be looking at more of a geometric aspect of line segments, areas, and volumes. Okay. So another interesting thing we can do is for going back to center of gravity, we can say, put a little asterisk here. I'm going to say we can relate center of gravity to density by the following. We should remember that if you have density, here, let me rewind that just a second. Relate center of gravity to, unit weight. Unit weight. Unit weight is like density by the following. We say gamma is equal to unit weight, and then we say gamma is equal to weight over volume, and so weight is equal to unit weight times volume. So if you were given a unit weight of something, of a collection of objects, then we can compute the center of gravity, because and if we know the volume of that, because we can relate these things, we can relate volume and density together through weight right here. Okay, so that's how we can look at that. And then similarly, we're going to say we can relate center of mass to density, say by the following. We use lowercase rho for density, and then we should remember that rho is equal to mass divided by volume. And then, of course, mass is equal to rho times volume. So if you remember, hopefully from a previous course, unit weight is kind of like density, except it's weight over volume, whereas density is mass over volume. Okay, and again, these can all be extended into, they're all extended into 3 dimensions. All right, so that's the background information, and in the coming